Welcome to the lecture 9 of EC 3030. So we here in this lecture we will be continuing on the MOS electrostatics, the discussion that we started in the previous lecture. So the topics that will be covered are covered in these sections in a textbook by Pire. Alright, so what did we talk about in the last class? So we talked about how the depletion layer is created, and when we get to a situation where this interface is inverted, then the gate voltage at which this inversion occurs is what we call the threshold voltage. Now one thing to note here is that, say you have this p-type semiconductor which is doped at a density of Na of the acceptors. So in this region the density of holes is Na and the density of electrons in this region is Ni square by Na. On the other hand, when we reach right at threshold, when we are at right at threshold, then the carrier density here is Na and the hole density is Ni square by Na. So this relation N equals Na and P equals to Ni square by Na at this oxide semiconductor interface is true only when the gate voltage is equal to the threshold voltage. Alright, so now let's get started with some quantitative calculations about the electrostatics in MOS capacitors. So first we plot the charge density as a function of position. Okay, let me erase this. Okay. Alright. So first we will plot the charge density. So at the metal oxide interface, the charge density will be a delta function because all the charge is piling up at the metal oxide interface in the metal. And then in the semiconductor, the charge density will extend only in the region of the depletion width, and it will be a constant with a value of negative QNA. So Na has a unit of per unit volume, and so multiplying it with charge gives you coulomb per meter cube. So this is the y-axis is charge density. Now, and this extends up to x equals to W, and this is x equals to 0. The oxide semiconductor interface is x equals to 0. So then what we can see is that the total amount of charge in the semiconductor will be Q multiplied with Na multiplied with W. So this number is, this is per unit cross section area, the coulomb per unit of cross sectional area. Alright, and then so this is the Q total, is the total amount of charge that we have in the semiconductor. So this is compensated by the charge that is in the metal. So the charge in the metal is simply Qm equals minus Q total equals Q NaW. So this is the strength of the delta function for the charge density. Alright, so the next step is to calculate the electric field. So here the y-axis will be electric field and the x-axis is the position. So now first note that here you have plus qm amount of charge and here we have minus qm amount of charge. So the electric field in the oxide according to Gauss law will be simply the charge we have divided by the permittivity of the oxide material. So epsilon naught is the permittivity of vacuum, and multiplied with Eox gives you the permittivity of the semiconductor material, of the oxide material, and this comes out to be QNA W divided by epsilon naught epsilon ox, and this will be constant throughout the oxide. So that's what we have here. So now what is the electric field at this point inside the semiconductor, at the oxide semiconductor interface inside the semiconductor? So that is the electric field at the surface of the semiconductor. Now to find out that electric field, what we do is that we know from electrostatics this continuity of electric flux, dielectric flux, and that is that epsilon naught epsilon ox Eox will be equal to the epsilon naught epsilon silicon. Epsilon silicon is the relative dielectric constant of silicon multiplied with the electric field in the silicon at x equals 0. So essentially the electric field in the silicon at x equals to 0 will be equal to epsilon ox divided by epsilon silicon multiplied by epsilon ox. Now typically epsilon ox, if the oxide is silicon, is of the order, it's around 4, and epsilon silicon, the relative dielectric constant of silicon, is around 12. So epsilon ox by epsilon silicon is about 1/3. So the electric field here will be around 1/3 that of the electric field in the oxide. So the whole curve will look like this. So it will be here, and the electric field will be 0. So it should be a straight line, and it will be 0 at the edge of the depletion width, because once you go past the depletion width, all the positive charge, all the negative charge in the depletion is compensated by the charge that you have piled up in the metal. So there will not be any electric field past the depletion region in the semiconductor. Alright, so this is what the electric field distribution looks like in a MOS capacitor, and this, the value of electric field at this point at the oxide semiconductor interface inside the semiconductor, this is also called the surface electric field. Okay, so now let's do the plots once again. Let me plot the electric field once again, because now what we want to do is calculate the electrostatic potential in the MOS structure. So here x is position and y is the electric field. And as we have seen, this curve looks somewhat like this, and this is W and this is X. Alright, so now what we want to do is calculate the electrostatic potential distribution in the MOS capacitor. So what we'll plot is electrostatic potential. Now what is electrostatic potential? So electrostatic potential is simply E equals, the electric field is a space gradient of the electrostatic potential. Now in the one-dimensional system, it's a simply ddx of psi, where electric field is ddx of psi, where psi is the electrostatic potential. Alright, so if we want to calculate psi, what we need to do is simply take an integration of the electric field. Okay, so the most important quantity here is the value of electrostatic potential at x equals to 0, and based on this integration the value of psi at this point will be simply, because it's an integration, the area under this curve. So the value of electrostatic potential at the oxide semiconductor interface, this is what we call psi s. Psi s is the surface potential, this is what we call psi s, and this is equal, this simply means the value of the electrostatic potential at x equals to 0, which is the oxide semiconductor interface, and this is basically the area under this electric field curve. So then to calculate that area, what we need to do is find the value of electric field at this point, and this in the previous slide we have calculated this. So this is QNA W over epsilon naught epsilon silicon multiplied with this side W, and this is the other side of this triangle, and multiplied with half. So finally what we get is the value of electrostatic potential for a given depletion width is this much. Alright, so now what we can do is we can basically calculate the electrostatic potential based on from the electric field through this integration, and if we do that, the entire curve will look something like this. So this will be a straight line in the oxide. Alright, so now we have calculated this much. The next step is to calculate, find an equation for Vg as a function of all the other parameters of the MOS capacitor. Now as you can see, if you apply a voltage Vg, then the voltage drop or the electrostatic change in the electrostatic potential across the depletion width is psi s, the surface potential. The change in the electrostatic potential across this oxide is Vox. Alright, and what we can write is Vg equals Vox plus psi s. Now what is Vox? So Vox is simply the amount of charge that you have across the two ends of the two sides of the oxide. So this is basically Qm divided by Cox, where Cox is the capacitance of the oxide layer per unit area, and this is given by epsilon naught epsilon ox divided by Tox, where Tox is the thickness of the oxide layer. Alright, and Qm is simply QNA W. So we get this equation for Vox. Alright, so if we just simply replace everything, then we get QNAW over Cox plus QNAW over W square over epsilon naught epsilon silicon. So this is the equation that we derive for the gate voltage for a given depletion width. Alright. Okay, so again, so we have applied Vg voltage. So the voltage across the oxide is Vox, and the voltage drop across the semiconductor is psi s, and Vg equals Vox plus psi s, and what we have derived earlier is that psi s equals Qna W square divided by 2 epsilon naught epsilon ox. Now let's write down this equation in terms of psi s. In the previous slide we have written down this equation in terms of W. Now we will replace W with psi s. So we can derive psi s equals twice epsilon naught epsilon ox multiplied with psi s over Q Na and the square root of this. So now Vox, what was Vox? Vox was Qm over Cox, and Qm equals Qna W over Cox. So now if we replace this, what we get is twice epsilon naught epsilon ox Qna psi s over Cox. Alright, so then we get twice epsilon naught epsilon ox Qna psi s over Cox plus psi s. Alright, so this is the equation for the gate voltage for a given psi s. Now in the next couple of slides what we are going to do is find the value of psi s when the system reaches inversion, and from that value of psi s, if we plug in that value of psi s in this equation, we can get the equation for threshold voltage, because threshold voltage is the voltage at which the oxide semiconductor interface becomes inverted, meaning that the electron density at this interface will be equal to that of the hole density in the bulk of the semiconductor, or equal to the acceptor dopant density. Alright, so now let's look at how to create an inversion. How do we create a situation where the electron density at the interface become equal to that of the hole density in the bulk? Alright, so as we have seen before, in an n-type semiconductor the Fermi level is closer to EC, and in a p-type semiconductor the Fermi level is closer to the valence band. Now let's say you start with a p-type material, and at the interface you want to invert it. So what you will have to do is apply a voltage such that these EC and EV levels shift down such that it creates a situation like this. So let's see how it does that. Okay, so here we have EC, EV, and EI is basically the mid-band gap, meaning that if the semiconductor had been a intrinsic semiconductor, then the Fermi level would have been here. So this I stands for intrinsic. Alright, so now this is a semiconductor that is doped p-type, doped with an acceptor, so the EF is closer to EV. Now as we apply a gate voltage, it creates a surface potential, and what the surface potential does is it pulls down EC, EV, and EI with respect to EF. EF stays constant, but EC and EI goes down, and as it goes down, when it crosses, it creates a situation at the interface such that EF no longer is closer to EV, rather it becomes closer to EC, and this is the case when the interface has become n-type. To say that again, initially before we have applied voltage, the interface EF was closer to EV, so it was a proper p-type semiconductor, but as we have applied voltage and when we reach the threshold voltage, then EF becomes closer to EC. Now at threshold voltage, how close does it become? Close does it have to become close to EC? All right. So to understand that, let's look at this picture here. So now this is before we have applied any gate voltage. So the gate voltage is 0. So the gap between the intrinsic Fermi level and the Fermi level of the system is what we call phi b. And also let's say this gap is x. All right. Now now here it's p type, and the density of holes is Na at the interface, and n is electron is Ni squared by Na. All right. Now at threshold, what happens is that this EC shifts downwards and EV also shifts downwards, such that the gap between EC and EF becomes equal to X. Or other words, now previously EF was phi b amount lower than EI, now EF is phi b amount higher than EI, and this essentially ensures that now at the interface the density of electrons has become equal to Na, and the density of holes has become equal to Ni squared by Na. Alright. Alright. So at the threshold voltage, the EC changes its position by an amount of 2 q phi b, and this should have been actually q phi b, 2 q phi b, and similarly the valence band changes its position by an amount of 2 q phi b. So the semiconductor needs to have a voltage or electrostatic potential of 2 phi b for carrier inversion. In other words, we can write that at Vg equals to threshold voltage, the psi s, the surface potential in the semiconductor, should be equal to 2 phi b, the phi b being the gap between the intrinsic Fermi level and the Fermi level of the system. And this will ensure that the carrier density, the minority carrier density or the electron carrier density at the oxide semiconductor interface will be equal to the majority carrier density or the hole density in the bulk of the semiconductor. Okay, so now let's based on the discussions the previous slide, what we need to do is let's find out an expression for the threshold voltage. Now what we have said is that at Vg equals threshold voltage, our psi s equals to psi b, and what we have derived in the earlier slide is that Vg equals to twice epsilon naught epsilon ox Qna to psi s square root of it divided by C ox plus psi s. So if we plug in psi s equals to psi b, then Vg becomes Vth. So then we get 4 epsilon naught epsilon ox Qna psi b square root over C ox plus 2 phi b. So this is the equation for threshold voltage. Alright, so now let's look at the band diagram. So band diagram for a MOS system means that the location of the EC, EF, EV in the semiconductor as a function of position, as well as the EC and V of the oxide and the Fermi level of the metal. Now note that in a metal you need to define only the Fermi level of the metal to describe the metal, and for the oxide you just need EC and EV. In an oxide the Fermi level is not defined, and for the semiconductor as usual you have EC, EV, EF, and EI is the Fermi level of the intrinsic semiconductor, which is basically just in the middle of the band gap. And phi b, so it should have been Q phi b. So Q phi b is the gap between the intrinsic Fermi level and the Fermi level, and Eg is the band gap, which is just EC minus EV. Alright, so now this is the band gap at Vg equals to 0, and at Vg equals to 0 so at Vg equals to 0 the Fermi level of the metal and the Fermi level of the semiconductor will be lined up basically, which means that at Vg equals to 0 our EFM will be equal to EF, or the Fermi level of the semiconductor. Okay, so now let's see what happens to the band diagram when we apply a voltage. Now this is the band diagram that we drew in the previous slide. So this is the band, the ones in this one is the band diagram at Vg equals to 0. So now on this plot we will also overlay the band diagram for Vg, for a value of Vg that is larger than 0, and for that what we need is to first plot the psi, the electrostatic potential across this MOS system. So as we have shown in one of the previous slides, okay, so let me erase all of it and then plot it again. Alright, so as we have seen in one of the previous slides, the electrostatic potential across the system looks like this. So this is x equals to 0 and changes like this, and this much is psi s. Then in the oxide the curve looks like this, it's a straight line, and this much is Vox, and then this is Vg, and the y-axis is psi, which is the electrostatic potential. Alright, now once we know the electrostatic potential, it's very easy to calculate the band diagram for that voltage, and what we need to do is that simply each of these energy values we will have to subtract Q minus Is. So for example, the EC nu, which we say prime as at the value of x, is the old value of the EC. Old value means at Vg equals to 0, and then we have to subtract Q minus psi x, and similarly the new valence band, this will be equal to EV x minus Q psi x, and the same goes for the new intrinsic Fermi level, and it will be EX my EI x minus Q psi x. Alright, so this is in the semiconductor region. So let's use a different color to plot that. Okay, so the way it will change is this. So the EC will look something like this, and this much is Q psi S. Similarly, EI will change, and this gap will again be equal to Q psi S, and similarly the EV will change like this. Alright, so this is the new band diagram in the semiconductor region. Alright, so now what happens in this oxide? So in the oxide the same will happen. So it will bend like this, so this value will decrease to this, and this much will be Q psi S, and then this will bend like this, as well as this will bend. So finally the band diagram in the oxide will look like this, and the EF will change by an amount QVG. So it will be like this. So this is QVG, such that, so before applying the gate voltage, EFM and EF, the Fermi levels in the metal and the semiconductor was lining up, but now the gap between the Fermi level in the metal and the Fermi level in the semiconductor is QVG. And note that the EF, the Fermi level in the semiconductor, does not change. Only EC, EF and EI changes when you apply a gate voltage. Okay, so we have drawn the same curve over here, just that this psi S should be all multiplied with a Q. Alright. Okay, so now we will see a number of simulations which show how the charge density, electric field and the electrostatic potential change as you change the gate voltage. Now here the gate voltage is 0, so there is no charge in the system. The electric field is 0 everywhere and the electrostatic potential is 0 everywhere. Alright, so now we apply a small voltage and you see that the charge there is some charge in the semiconductor region here, and that creates an surface potential here, and so it creates an electric field inside the semiconductor, and it goes down to 0 very quickly, and it also creates a surface potential in the semiconductor, and the difference between the electrostatic potential at the metal and deep inside the semiconductor, this much is actually equal to Vg. Alright, so now if we keep on increasing, what you can see is that the deep width of this depletion region, the extent of the region where the charge is actually changing, increases. And as you keep on increasing the voltage, the depletion region will increase, but you see the magnitude of the charge is actually constant. So this is a depletion charge. And now finally, when you reach a certain voltage, you will see that there is this charge picks up over here, and this is actually what is the inversion charge. Alright, now if you keep on increasing the voltage, this inversion charge will change, but the extent of the depletion width will remain almost the same. Now another thing, the calculation that we did there, we assume that the edge of the depletion is sharp, but in reality, in simulation also, in reality this edge is not sharp, rather it's diffuse. Nonetheless, our simplified model of the MOS system is valid in most cases for calculations. So the approximation actually gives results which matches very well with experiments. Alright, so now
let's look at how the band diagram evolves as we increase the voltage. So this band diagram is when the gate voltage is 0. Now if we increase the voltage, we see that the EC/EV all shifts, and as we keep on increasing the voltage, the band bending inside the semiconductor also increases.